Arrhenius equation to calculate the K at one temperature from K at another temperature. So if you just have some concept that if you can make a test tube hotter, then the molecules will slam together faster and the product can be made faster. So usually the higher the temperature, the faster the rate. You can see here I've got a chart. As the temperature goes up, the rate constant goes up. All right, so that's just kind of some basic idea. Well, if you want to know specifics, you need to use the Arrhenius equation. The Arrhenius equation is going to give you a couple different pieces of information. It gives you the activation energy, so you can compare. If you change the activation energy, you can compare change the rate, and if you change the temperature, you can change the rate. So you can see as the temperature goes up, the rate constant will go up. So if you're going to compare two temperatures, you're just going to make a ratio. So here I've got whatever the second K is that you're asked to find two different temperatures. And so it's K2 over K1, just making a fraction. And then I've got the Arrhenius equation on both of those and just make it equal to a fraction. You can see that your A cancels, and essentially you've got e to the negative activation energy over RT divided by the one at the new temperature. So when you rewrite this, and this is ugly, I hate this algebra 5 or whatever it is, but when you rewrite the equation, this is the one that I would use, or this is the one I would memorize or write down in your book of formulas, so that you have K2 over K1 equals e to the EA over R times the quantity 1 over T2 minus 1 over T1. Okay, so now you have a new equation. Now you're given the rate constant at the lower temperature, so you're given K1, so we'll fill that in just a minute. So really what I need is to find my second temperature and my first temperature. They give it to you in Celsius, and so I want to make sure I put it in Kelvin because no math works usually in Celsius. So as I put these through, I'm just going to, they've given us the activation energy. So I have negative EA is negative 18 kilojoules per mole. My R, remember there's a couple different R's. I'm going to use the 8.314, but 8.314 is joules, moles over kelvins. So that means I need to get kilojoules into joules. I need to change them so that they'll cancel. So I just recopied this as 1.8 times 10 to the 4 joules per mole over my R, and then I simply took a calculator, 1 over 3.14 or 314.15 minus 1 over 412.15. Got it as a decimal, just wrote it as a decimal, and then solved it as negative 1.63997. So it's just a big bunch of numbers. You multiply, divide, whatever. So when you put them together, I've got the K, which I'm trying to find. That's the one at the 41 degrees, divided by the K at the lower one, which they gave it to me. So 5.2 times 10 to the 5 equals e to the negative 1.3997. Right. So I simply found. I just put negative 1.3997 in for e. E to the x, so just hit the e to the x button, which is usually a second function ln button, times my 5.2 times 10 to the 5, and solved for k. And I ended up with 100871. Okay, so when you do that, that's too big of a number. I never trust a big number like that in for Aleks. So I want to make it smaller and use scientific notation. So they wanted two significant digits, 1.0 times 10 to the 5 And then for my K, it's over molarity times seconds. So I just put it on top. M to the -1, S to the -1. Okay? Ugly, ugly, but it's really just ugly at the beginning, and then once you have the formula straight, it's just insert it and solve for the unknown. So hope that helps you.